last time it had to be quite. Time, yeah, and I successfully kicked out my microphone from the cord, so yeah, that was success, definitely. Yeah, hopefully it will somehow be hearable. We'll see. Hello, Super Dialogue. How is you today? Oh, you were using probably different name back then, weren't you? I kind of think I do remember a lot of people from those days. I'm working on basically the few last evenings I spent on reading the marvelous Intel manual for their 64 instruction set, which is the same as AMD. Oh, Andre Medeiros, right? I do remember you, man. How can I forget, man? I do remember, don't worry. Don't you worry. Or maybe you are lucky enough to be in those 3 people that I kind of remember from those days. That actually worked with us those days, yeah. Yeah, so what I'm trying to do is basically be able to generate instructions for CPU in memory, so I can basically run them, and I can at real time or runtime generate code and execute it by a function call. And it takes a little bit of magic in understanding, mostly in understanding these kinds of things from Intel. And I think I understood enough and wrote it down here, which I can paste here because I think it's public. Not sure though whether the repository is public or not. But it seems like it's public. It doesn't say it's private. Yeah. So I wrote it down here, all what I learned about it, and actually I already had like one version of it, but I think I fucked it up, and I said to myself that hey, maybe I can just rework it from scratch and implement some things for the API that I want. But in general, where I want to get is to be able to basically do a simple thing, which is something like this one. A simple example would be this one, which will produce, I think I will use a structure for those instructions. So it's, I'm using incorrect naming, so if I include what I wrote so far, at least some of those types should be, at least the enums are there. So what it will do, it will basically give me this inst object, which is instruction, which will inside contain 2 simple things. I can already actually write it down, and I want functions to be later, so I will make a separator here. So x64 inst will be simple object composed of several things, basically 2 of them, which will be some bytes of some size, and and I think I already have it calculated in the previous project, somewhere around here. And there is somewhere the calculation of the maximum size for an instruction. Yeah, there I want. SDM 2.1, basically in the manual 2.1. Yeah, it's basically here. Yeah, so I'm counting, I read it somewhere, the number of maximum prefixes that it can have, and I read that it can be up to 3 maximum. So I'm using that, but yeah, I will move this to my other screen, the old version, and I don't want it to bother me too. So I need the calculation here. So this is a fixed buffer, fixed size buffer, that will hold the bytes for the instruction. That should be enough. We will see. I do have checks everywhere, so that should be okay. And then some integer that will be a count or something like that, which we actually can do like a really small thing. So what it will do is basically this function will eventually give me correct instruction for these arguments. So in this case, the instruction should be when disassembled, it should be something like this in Intel notation. So it basically the target actually is to have to have like it can be used for JIT, because this you can use this for generating like a CPU code at runtime. So you can, whatever you generate, if you have a language compiled in the memory and you are watching it while it's running and want to help it not run it to virtual machine, what the JIT would do, then you can translate that virtual machine bytecode to CPU instructions, what JITs generally do, and have it running that way. Probably eventually I will find some library that is doing it well, and I will drop this one. But until I find something, I want to understand, because I don't like using libraries without knowing what's involved, because then I cannot judge how the library is doing things. Oh, awesome. Yeah, so I need something that will be really tiny and will have no dependencies. And I need, I will eventually use it for this experimental language that I'm working on. So that should be, yeah, let me pull in these. Yeah, so that should be used there for similar purpose, but I think I won't need like full library, every possible instruction in there. I just need a few of those, I don't know, a handful, like I'm estimating around 30 instructions for base thing, and eventually maybe some extra special ones for optimization. Fire Drake, hello! Yeah, ISM JIT, yeah, this I have it already somewhere on my notes. I've been looking into this one. ASM JIT, yeah. Yeah. So I probably will eventually use these third-party libraries as a reference, but for now I just want to have it really. Yeah, and it's CPP, and I don't want CPP at all. Yeah, I remember this one. Yeah, they define a lot of operator overloads and whatnot, so they allow you to. So they allow you to generate much simpler code, like use much simpler code than what I plan to do. But yeah, so I cannot use CPP because all of my projects are now in C only. Kind of a mixture of C99 and C11. So yeah, whatever Microsoft supports, because I'm still using Microsoft compiler. So yeah, what I plan to do is have these as a last resort if I won't be able to find it in the in the other references and manual, I will probably, or by actually reverse engineering things, then I will probably look into these for reference and other things. So we need, for the tooling, I will need some disassembler, and this is the one I'm using for now. I don't even know whether I should know this guy. It looks like somebody who really knows what he's fucking doing. So how it works is simple. You put some code in here and it will give you the actual disassembly. So this is what I will be basically doing, except I won't be inputting with this, with normal assembly language. I will be inputting like this, with C functions and macros and whatever. I want it to be smarter than usually, what people usually do. Let me just put I want it to be smarter, so for example mov instruction has several opcodes that you can use, like the 89 in this case, because 48 is prefix for 64 bits. 89 in this case is just one of those, and there is several of them, I think around 10 or 20, somewhere in there. And also I haven't done this before at all, like just over the weekend I was looking into it and I was able to run some code. But that's basically my whole experience with this, and I was a little bit dealing with some details like calling convention things and those things, and a little bit of code generation. But that was generally generating just instructions, and then I would compile them. So I don't know how the CPU exactly works, what are the pitfalls. What I'm trying to do is to understand it, and as a part of that, I'm trying to implement this little library to capture whatever I have learned, and also made this little write down that will help me understand it in the future as well. Yeah, so we'll be using this assembler, and we know that this code already produced these 3 bytes. Yeah, what I can pull up is probably because I wrote a testing function for these. Testing function that is quite simple. Oh, this one. Yeah, it's this simple thing that I will just put here. Yeah, so what this function does is basically takes in it's wrapped in the macro, so it takes 2 things. It takes this thing, so I can write x64 test. I will not be storing that, and yeah, and then a string which is in this format as well. I will just put it here, and what it will do, it will basically test whether the function returns what I want, and that's the whole idea. Eventually I want to get to be able to produce at least this code, which will be quite simple, to be honest. At least this code and read, and be able to put it to memory, mark the page where it is as executable, and directly call it. And that would be basically the first step in making it actually work. Probably need, and I'm now trying to not use any of my base code, because I want this library to be completely separate, and only use probably headers that have no implementation, that are really just type headers like stdbool and std. Yeah, so that's the idea. So we can actually make the tests work. I will use tests a lot here, so we can do x64 instance. My language will not target the x64 assembler, because I still have problems with how to name things, to be honest, because I think assembly code is is this. It's like this human readable format. But this one is called, how is it called? I don't even know what the word is, because I had a quite busy day in the work and I'm tired as fuck. So yeah, this one is something different. It's what assembler basically produces for you from human readable instructions. It will produce this one. So I'm targeting this one. So I want to produce these 3, 4, 5, 6, 7, 8 bytes for whatever instruction I put in. I want it to be, yeah, that's a thought I didn't finish actually. I want it to be smarter, so if I want to do, for example, because this first one will put contents or value in RCX register to ArrayX register. But if, for example, I want to do this one, which means that put contents of a memory pointed to by RCX to ArrayX, and this thing I think is written like it's a keyword PTR. I think this one will be correct. Yeah. This is for example the next one. This is first step register to register. Second one is register or memory to register. And then you can go crazy from there. This is one version, so you are able to add like a constant to the address in RCX, which can be of two types. It's either 8-bit or 32-bit. So let's say we put them like this. So this can be encoded as 1 byte, and this must be encoded as 32 bits, which is 4 bytes. So yeah, we can see that it's already there, right? You can see the offset here as 1 byte, and this thing to be here as 4 bytes. So these are at least few of them. You can it goes on and on. You can do a lot of things with these. Actually, you can do, I think, this one, and you can do also this one. Yeah, these are all valid expressions. So you can go, and this is, I think, the maximum you can do, if I remember correctly. Some samples. Yeah. It's basically the most you can go, the most complex expression as far as I know. Yeah, so slowly we will work through all these simple things to this most complex thing for just a move instruction. That's all we do for now. So yeah, I can already actually take these in and write the tests for them. That would be quite nice to have at the start. I don't know what the final syntax will be before I use something that was it was almost perfect, and I will show you what I meant by it being smart. A bit more than what usually people do. Because usually people do know how these things work, and they can anticipate various special problems, which I guess eventually when I write this library I will be able to tell them too, and it will partially invalidate most of the smartness in that library, and I will have to write something more explicit than some guessing machine. But basically the idea is that instead this thing should say that I want a register as argument 1 and register as argument 2. So in this case we want register as argument 1, but we want memory. I call it usually this way, where the base is RCX Then we have no index, so we can go x64 none. For index, we have x64 x2 scale. This means that it's this times 2. And finally, we have some displacement, which is 0, and this one will be like this. Eventually, I want to be able to write just these. Like 0, 0, 0 means that it's just RCX base, and I want the address that is there. That will be there. And the function, the x64 function, should be able to understand what I mean, what I want, and generate the code for me. So in this case, it should generate this little thing. And so we can go further with these tests. Again, RAX, we want RCX as base, but now we want smaller 8-bit displacement, which is I usually write it as the last parameter. So this will be the second thing. Then this will be with a larger than 8-bit, which means we will automatically have to go for 4 bytes, 32-bit placement. And here we go, here we have RDX as an index. Usually they use it here, RDX. And we have still 400, still this large thing at the end. Yeah, and I need to paste this one here. One is the same, is it not? Yeah, because I will. This one is with a scale of 2. I can just put here that scale of 2. x64 times 2. So it will map basically almost precisely to how it's written. So RCX plus RCX is a base, so RCX has a base address. Then we add some indexing operator, indexing register, which will be in this case RDX. We will every time, we will basically multiply it by 2, whatever number is here. Whatever the index is, we will multiply it by 2, and then additionally add 400 as an offset. So yeah, now I see that I don't have these scales yet in, but that's okay. I will just write the scales thing because I don't want to go further. I want to first write an encoder for this thing. But I can actually explain it a little bit using this document that I wrote. x64, and this would be scale. I want this. I will use. I'm not sure. Yeah, C won't help me anyway, so I can just do this. X2. First is x1, and we only can use these 4 scales, nothing else. So if it's 0, this would be 0, this would be 1, this would be 2, and this would be 3. Okay, so but we will get to the scale later. So for now, yeah, and the one final thing that I need to start is type of enum for opcodes that I will be using. And it's x64 opcodes for MOV, rec, rm. Yes, I do remember these for some reason. And this one is, we will do just these 2. I do remember them because I wrote them just a few days ago in this thing. So what we're gonna do, and what I want to do here is x64 mov, and I want x64 operand destination, x64 operand source, And we need operand thing as well before API. Where should I put it? Sooner than that. I will leave it here. No, I will leave it here because instruction is the last thing you want to do. So this operand will be, it's not anything that exists on the CPU like the other things that I have here, like mod RM. This is direct representation of a byte that is used for things, but this operand will be used only for this high-level API. And there will be x64 operand kind, and this would be x64 O register or memory or immediate value, but I won't do the immediate value right now at all. So it means that, yeah, finally we will have those, and these two macros, x64R and x64M, basically just generating this operand structure. So I will write those, which is x64R, and it takes the register, and it produces x64 operand structure or value with the kind being x64O register, and the register will be whatever the reg is set to. So that's the first macro, and the second macro is we want base, second is index, then it's a scale for the index, and finally we have displacement, and this will be mem. So memory location, mem.base is base, mem.index is index, and mem.scale is scale, and mem.displacement is displacement. Yeah, that should be enough. Okay, so now these macros should work, I believe. Okay, for move, okay, and finally we need this one, yeah. So we know that there is some kind, operand kind, and then we have union. This would be x64 register for register, and struct for mem, and we have for mem we have base, which is register, x64 reg base. Second is index, third is x64 scale, and finally displacement, which is maximum of 32 bits displacement. And I'm not sure whether the displacement, I would expect it to be signed, but for now, is this supposed to be signed? So we will see. I'm not sure whether this displacement is that. So when it comes to encoding these instructions, what I learned, it's quite straightforward once you understand how it works. At least I hope it's straightforward, but it may be not eventually. So there is opcode, which will tell you only partial information about what it is. So if I open this one and we'll go to, where was it? Programming guide? No, probably even this one. Instruction set reference. Yeah, so we will go for MOV instructions, and here is the table that says the opcodes for various types of MOV. Quite a lot in here, but we are interested in this 89. This is the first one, and second one is 80B. So what this says that 89 means that on the left hand side you have r/m 16 and on the right you have r16. Oh no, I want the 32-bit version, yeah. So on the left we have something called r/m, on the right we have something called r. And the ATB is the same thing but in reverse. So on left we have a register, which means that this register is the target, and maybe I can zoom it in a little bit. This register is the target, and this r/m thing is the source. So this is destination and this is source. And here destination is this one and source is this one. So I probably have it the other way around in my documentation anyway. Yeah, because this is incorrect. So here, just fix it. This is 8B, and this is 89. And wherever I set 8B, need to reverse that. Just B, and this is 89, 8B. So be 8B, B. Yeah, I fucked it up. It's pretty. Again, I want all these things to be called x66 and these to be called 89, and everything that this will be called OXAB. Okay, so the thing is that yeah, I will explain what the thing is. Boop, boop, boop. Don't save. So the operation code will tell you basically what the order is in case of MOV. What the order is of these two arguments. One is register on the left and RM thing on the right, and this has RM thing on the left and register on the right. What this RM thing is a special byte that follows. So we have the opcode. I will put this somewhere here. We have opcode, and then we have one byte that is basically called mod RM, and this one byte encodes some additional information. So opcodes tell us what the thing that is doing actually, and it will tell you what the order is. But this mod RM thing will tell you which arguments are there. So we need to get to mob rax rcx. This is what we need to do. Opcode tell us that rax we can use simple register on the left, why there is a register, and we can use something more complex on the right, which is RM in this case. So this mod RM byte encodes 3 bits of information. It's mode register, which actually is the same as the register I wrote there, register, this one. So we already know that we should set the register to that one. So we have some kind of opcode 89, and then we have 4, yeah, and this is 0x, and we know we have some bytes. So first 2 is some kind of a mode, we don't know, but the register we know that is index, and it's basically in the table, and it's in this order. It's almost perfect, but it's A, C, D, B. It's not in alphabetically ordered, so that's a little bit fucky. We want rax to be the register of that, so these 3 bytes in the middle. So this is mode, this is register, and this is something extra, so we will call it E. Yeah, so we know that this needs to be 3 zeros, but we don't know what these things around are. So we will go further and we find out that what the mode values are. We can have these 4 different values, and this will say value and register and mode RM, which is the last one. RM taking the last 3 bits is treated as memory address, so we don't want that. This is same as above, this is also same as above, and this says that if first 2 bits, the mode is actually 11, value and register this is incorrect. Yeah, this says that this is basically telling that the RM should contain the source register in our case. So we know that we want RCX, and RCX is the second one, is this one. So we need to put these 2 bits here and this value here. Okay, we can check what this is for a value. And this says it's C1, so it's 89 C1, and that should be it, right? Because there is no extra values. We already said that, hey, we want this to be the AX, and the mode we want the register to register operation, which is set by these 2 ones, and the final argument, like these last 3 bits or first 3 bits, depends on how you get it, are the source register, RCX. So this, if I put this here, it should do almost the thing that we want, I believe. Yeah, except it's not RCX, but it's E. It's not R. That means that it's only 32-bit. And that's like a second part to this, that we will need to make sure and tell it that we want 64 version of it, and that's quite simple because you only add like 1 extra byte at the beginning that is specially encoded, but that will basically switch it to 64 4-bit mode. We'll use 64-bit register. So yeah, that's the idea. So in order to construct this mode RM byte, I already have like a mode register, the RM values in there. And now I need to put input logic that in case both destination and source are registers, then we are doing this simple version, which is basically just opcode plus and the mode RM, and that's it. We are done. Yeah, so we can try it out. What I did before is this extra thing that I call x64 operand pair. Get operand pair, and you give it to AB. How did I do it? Don't remember. It just combines the 2 things together. That's it. So I will check my older code. The pair. Yeah, just like this. So it's we'll move value of A, shift 8 to 2 bits left, because we don't have many bits occupied. We only need 2. We can do 4 actually, and then do OR with B. That's it. It should be then it should work. So switch x64 get operand pair day count as count, and case x, we'll call it pair 64 o pair. Yeah, that's this would be x64 operand I call it just O register. And register something we will return. x64 instance 0 default equal to x64 fail. Actually, I will use my library. I don't care for now because I already have a lot of things in there that are quite useful and will make it much faster, I believe. Yeah, it will make it much faster. I have tons of code. It will be CO fail. So x64. We'd like. Okay, you can go here. Let's try it. We'll see what will happen. Cannot open include file. Okay, that's fine. This is just freshly set up, I think. Need to find out. Oh, I know why is it. Okay. I will need to fix my paths because I have them hard coded, but this project ugly actually. Orbit. Build. We'll just do push local includes. Yeah, okay, just do it like this. This is all we need. Go even higher than this one up. How many up I need? Did I even open the correct one? 64. Here. I'm not checking on the chat. Nope. Not getting anything good. Music going is good. So we need to go. We are in a build directory. So 1, 2, 3, and then it's RT. That's COH. This should be the trick, but I need to pass it in, right? If my builder, yeah. Getting some readable errors. Yeah, these things I forget all the time. x64 dump. Yeah, I probably will need to bring in my code for bright. And a few lines, x64 dump. Clear in the tests probably. Although we can probably just do this little thing. Port. We can define these things up, right? CO fail. So we don't have to even have these things right here. Yeah, and we'll do the trick for us. x64 test dump. Now we have libraries clear, and we have optional for error. Okay, and we are now missing for testing the main. Equal. Yay! Hey, I'm here. So left kind is register, right kind is register. Awesome, and we are jump right on top. Great. So that would be first thing. Okay. So if it's register to register, we know we need to produce instruction that will be. I will start writing it as I would if I didn't know where it will go. So we know that we need to encode 89 ATB 89 ATB remember 89. Yeah, 89. So this is by the manual. Take the manual because that's the best. 89 is for, and we want ATB. So this one is ATB, and this is 89. Right. Good. So I will grab this one. So we know it's this one. And then we need to just encode x64 mod ARM. I will probably don't even use the picture. I will keep it because I think there will be cases where let's use it. And we know that mode should be the 1.1 mode, which is this one. I already have them listed here. The mode is direct, the RM is target, so this is register -1. I'm doing the -1 thing here because what we want is I'm not having array_x as 0, I have it as 1. Because I want to be able to specify that I don't want any, I don't know, scale, I don't know, index base register. So the logic will be able to detect that. 0 was used for array_x, used in the, and then the register. We know that we are using register RM. That yeah. So register should be on the left. This is our target. So we know that RM is on the right. We know that we can write it in that order as well. The register -1, this one, and yeah, and the count is 2 for now. And that should actually do the trick, if I'm being honest. At least for the 32-bit version, because we are not yet have any way of driving size. Have to go. Okay, so we get here, and then we get here. We will see what, so this will just parse the string, and here we will print it out, the expression. Expected is this one, and what we wrote is, it's not even, I know we are missing the, this is interesting again to me because I'm not sure what version and what code. I'm not sure what this assembler is using, but I guess if it's this one and it's C1 that we did actually by hand here, We did it correctly, and we put RM as CX, and we know that 89 is that one correct? I think I'm mixing these up because I mixed myself so badly during the weekend, and I need to check it out. So yeah, we are doing it in 8B. Now we will get correct order. Yeah, now we get in correct order. EAX. EAX, ECX. Exactly what we want, what we expect from. Should be 8B, B, and we want it. We don't have the 64 version, so that's okay. So I can just simulate that I want the size x64 S32. For now, let's just define the sizes. Sounds good. x64 size 64, 32, 16, and 8. Okay, and I will probably want to move these. Because these are closer to public functionalities we will use. These one are just internal things. Okay, so I think we're almost there. If I will do 32, then this one wouldn't be there. We still need to find out why it's C8 and not C1 as we calculate it. So C1, yeah, because it's the other way around, so this should be C1. I will comment this out because these won't work anyway, and we want to go step by step. Good. Yeah, where is... Here it is. Okay. Wrong with you. Syntax error. Why is it syntax? Oh, right, because we have someone else. Okay, fair enough. It's not publicly used, so this one should go. Because people won't be using on the outside of the API, they won't be using these, but I will write them down in here. Can actually int to x64 operand. Okay, what's the x64 size? I'm not sure how I will do the size. I was thinking about doing it here, like mode 64, mode 32, 16 and 8, but I don't think that I like it. Okay, so you run it. We want 8B here. Okay, 8B C1. One we want. Yeah, it is. Okay, so run it. Yeah, we have the first one. I will first do the 32-bit, probably. probably the best option right now, and then we will do the other thing. So now we want to do, instead of value ECX, we want to use it as address and get the memory contents from it, which is actually keyword ptr. So what we want from this is, calculate it again, so we can try. So we know that it's the same thing, it's 8b, first one. Then we need to put in the mod rm thing. Here, 8b. And now we want the, we don't have any displacements. So if I go to documentation, the mod, the value on register mod rm is treated as memory address from which a 32-bit value is loaded to register mod. Yeah, so we want this one definitely, because this one is same as above, except we now need to provide an 8-bit value for displacement. Yeah, so we want 0, 0, and we have EAX on left is 3, and we have EX right is 1, 0, 0, 1. So this is, and this should produce the things, so which is 8b and 1, right? 8b and 1. If I put it here, yeah, correct. So this is what we need to do. Basically, we will just do almost the same thing as we did before, but we need more logic because there is something else involved. Well, so if it's case x64 O pair, and this is x64 O register on left and memory on right, then we need to do something else. And I will do it in a separate function, so I will call it emit binary, and it will pretty much just get all these things as the one before, and basically do this here. Yeah, and this will directly return. Okay, put this here. And we can get rid of this one. Hopefully, I like how it had before. I will need to be. It will need to be. Yeah, the in and ones commas. Yeah, it did. It did badly. x64 inst. We will zero it out. I probably don't need to zero it out, but I will do it anyway. Cheers. So we will have this IT pointing to bytes. It means that we can just do this instead. So we will write the opcode. We will write the mod rm thing next, and that's it. We can break right here. And finally here, we will need to bring this back. And finally here, we will do inst count is inst it minus inst bytes, and that should do the trick for us. Yeah. Break. I will need a block here anyway, so I'm not sure why I'm breaking that way. Okay, so here we need to do same thing, and it will be a little bit problematic because now we are depending on these two constants, and we want to be not to depend on those two constants. So what we'll do is I will do struct x64 op. I'm not sure if this will survive like the entire thing, but I like the idea, which is taken from Per Wongson, who did this. So we will see. So we had like this structure with variants of the codes, the variants of the opcodes for various for the various signatures or ordering or whatever the function will need. I don't know the entire set. I only know basically the two mobs, how they work, but I don't know how add works, for example, or sub, but I saw him using the structure successfully for those as well. I will do the same because it will solve my problem right now, but it will probably create problems somewhere in the future. And we can call this static op. And I trust Per because he knows what he's. I will do it the same way. I don't care. We will put the mob in here and yes. I think this is more like implementation. We will see. We will see. We'll see what will happen there. x64 up mol. We will pass this here. He will grab it. And we will just put it here. Actually, REM, so we know, because we are putting destination on the left, the register. We want this one, and here we want basically the same thing. RM. Okay, that should solve us. Let's compile. Okay. Test whether the first thing still works. Yeah, it works. Okay, now we do the second thing. Now what I usually do is I have like this if 0 that I technically move as far as I need and keep the tests there while I'm working on a new feature, and when I stop working on it I will just enable the test and be done, and the same for future things, future features. So this is basically like a cursor in the middle that is tracking the current progress. Okay, what we want to do here again is that we want to use 0, 0 for mod RM, but there needs to be logic, right? Because now the second operand, the source operand, wants memory, and the memory is more involved. It contains, it has base, index, scale, and displacement. So we can only do the simple thing that we did here, only in case we don't have any displacement. I mean, we can still do it with, no, the displacement must be 0, so let's do it here. 64 operand. Or keep it open here. So displacement has to be 0. Base needs to be not 0. index must be 0 and scale has to be 1. Well, we don't care about scale as long as index is 0, but then yeah, I will still validate, because if somebody will forget the scale set something else than 1 and we'll have index as 0, then there might have been some bug from him, so we will make sure that scale is 1 in that case. So we can do it simply. If base is not 0 and index is 0 and scale is 1, which is the value of 1 is 0 actually in this case, and as displacement 0, then we can go for thing which is IT++ is OP x64 mod RM encodes. Now it seems more like I don't even need that structure at all, because I can just do simple arguments here and make my life easier, because it seems like I will be calling these things, or I don't like these other structure, so I will just think completely, yeah, better. Encode. Yeah. This one. So this will be indirect. Because indirect those 2 zeros, and so we have covered this one, we have now covered this one, and we need to cover these 2 after that. So I guess this code will change, but because whether we go for indirect or the ones with the displacement, it only depends on whether displacement is. So we will go indirect, then we want the destination register and the source register -1. And that's it, I believe. But the source doesn't have a register because it's a memory, so we need base -1. Yeah, and this should do the trick, so let's give it a try. 8BC1, but it's not 1. This one. Yeah. Now let's give it a try. Okay, this is standard. You wait. Yeah. Type. Dirt. These are going to be removed. Load. Oh my god. Base. Mem displacement as well. Let's go. So first, does it jump to the right one? Doesn't. It. Oh, need to put this here and 0, 0, 0, 0. Right. Not too many zeros. It's only 4 arguments. Okay, there again. Yeah, win. Now we put in the byte for opcode, and now the mem base. This is RCX, so it's not 0, it's 2. Index is 0, scale is 1, which is 0, and this placement is 0. That means we will produce the thing, and we can check whether it returned 1. Yeah, so we go back, and yeah, so we passed, we generated correct code. Yeah, let's test the previous ones as well. Yeah, it works. So 2 passing right now. Go on, but I will need a short break. So I'll be back in a few or so. Okay, so next one we need to go is so we have covered. We have not done the 4-bit ones, but we will do this one. This is the next, and also we will do not the same. That's just the displacement of two different sizes. So we want the displacement to be 0.4, and here we want it to be 400. Good. So what we need to do here is this additional logic. What I will do, because here displacement doesn't make sense, and I will do it differently. So we can here decide by the size of the displacement what we want to do. So if the displacement is 0, I will do it this way for now, but I know it's not super correct because we will need to change it, because there are cases where you want displacement to be 0, but you want index scale and the base to be something concrete, and setting mode to indirect, which in this case indirect. So I can have 8 mock RM mode. Mod RM mode is, yeah, it's indirect. It's the same thing. We can do it like this. If S-man displacement is lower than 256, we can do it like this. If we're doing hexadecimals otherwise, so if it's lower than 256, then it's indirect displacement. I know I need to check whether I called it that way or the other way. Yeah, it's this displacement. And SMAM, otherwise the displacement is there and it's 32. What this will give us is that we know at least that displacement is required to be one of these values, and that is set. There is a case when displacement is 0, but we cannot encode it with indirect. We will have to force it and output it either with this 8 or 32, because there are some cases where you need to do that. So we can just simply remove this condition here, and what we can do is we can output placement here. I don't have a function for that, so I'm thinking how to do that, because it would be nice to have some simple function to these things. Thinking what we want to do is this RM mode use here. I don't think I will ever support really Indian architect, so I can much go. Okay, I will do it the other way. We'll do it the other way, and that's implementing a simple function that keeps inserting. Well, that wouldn't work. So we will write the function. Yeah, we will do the function. Emit writes. We'll give it this one. Return the pointer, give it pointer, and we'll return one. And we can do it. it this way. Write these 4 bytes, and we will supply the we'll force it to be 4. I'm thinking about how to write it, not completely it. Because I will need to do additional switch case here, which I will do. I don't care. Note case indirect. Yeah, I will do it like this one. If it's indirect, this 8. That's 1. I'm not sure if I will be getting the endians right. You don't want me to do that, because I will just debug it and call it a day, because to actually be able to brain it out. So this will be a pointer, and we will return a pointer to bytes IT, and we want the bytes int bytes count, and we will just do while bytes count IT plus plus is equal to bytes plus plus, and return IT. Okay, so this should technically work. If it compiles, of course. So we will see. At least one. There has to be at least one. Okay. So. Okay, this works. Displacement is now 4, so it should go to this 8. That's correct. We are going in here, that's correct. And finally we write, 1 byte, and now we will see. I think it's correct. It though. Now let me show the bytes. 4 of them. Yeah, and the 4 is first. Okay, so it works. I got the endian right, and down here. Oh, and it doesn't match, but question is, I've left the original string here, so we need to check whether it's correct. And this time I won't be doing it by hand, but I will just try this one. Yeah, it's what we wanted. Yeah, it's RAX, move RAX, EAX, 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 CX, 2 words, because we are not 2. Yeah, so it's correct. The first one works. Let's do the second one. So now the displacement is larger than this. We have it on 400, so we will be writing 4 bytes. We jump correctly. Okay. And of course it doesn't work here, but yeah, at least we know that there is 81 and here is 41. That means that that it was picked up correctly. And here we go. Yeah, so that works as well. Okay, so we have the displacement in. So for now we used only this. This is as much as you can do, I think, with mod RM. There is one special case that we can probably cover right now. So here, special cases of mod RM. There is, when you use ESP, it has a special meaning when the mode is one of these 3. And so is EBP. When we are using EBP with this mode, it has a special meaning. And the special meaning is that in case you're using EBP as a base pointer for the address modes, it will work differently. It will basically, because if you want to use, so what it would be in here, it would be something like this. It would be EAX, but we would use EBP here. And this would produce something quite different. What we would expect. So let's give it a try. It should run through the code that we already have. Yeah, we didn't update the code here. Okay, update code here. It's done. Okay, what we want it to be is using uppercase everywhere else. It's okay because the equals will actually convert it to bytes, not the other way around. I could have made it the other way around and compare the strings, but hey, probably I will have to do it because with larger sequences that I will do and will compare them, I will want to compare the strings so it can tell me where exactly is the difference. Focus only on that part, but we will see. Okay, let's click through whether the stream is going okay. It seems going okay. Okay, so it goes okay. Seems profile image can take. Oh my god, Twitch, just don't tell me things I don't need to know. Yeah, we will keep it with this large displacement for now. Probably we can, yeah, we will go in. And it will produce this one. It will, of course, produce an error, which is actually a good idea to have it like empty. And then you will see the difference. Expected will be empty string, so it will always fail. Expected. What do you call me, bitch? Well, is A85 here? It's one, right? Let's run it again. I have some bug in there because the expected shouldn't be this thing. Expected, setting it to 0. Okay, I will go through that code because it seems like when I keep it as an empty string, which I was just bragging about, so it's an awesome idea. And -1. We'll skip this, expected, this one. Buffer. Oh yeah, I'm not resetting the buffer. Yeah, I will just do it immediately here. Yeah, I didn't reset the buffer because it's static here. Which probably I shouldn't even like have it static. Why is it static? I can just tell you to be zeroed and don't care and never 0, and I don't have to deal with these things. Somewhat high level programming. We are returning the buffer. Yeah, we cannot. Oh, that's why it was like that. Okay. Fair enough. Because we are returning it from the function. Okay. Yep. Yeah, and it's great. Okay, so this is what is produced, and it actually works, but it's not what we would expect. It wouldn't be this. At least I hope. If I understand it correctly, then it won't be this thing. But, and I will tell you what it will be. It will be this. Something like this. It will be probably padded with zeros or something like that, but I think it will be this. If I understand it correctly, so now we will check my... No, just there. It's just there and it says RBP for some reason. So I don't understand it correctly, and that's why I need to go back to drawing board and find out why I did not correctly. So by the documentation, if you use EBP in the mod RM, which we are doing here, here, go through the code again and confirm that that's what it's doing. Now we are going to mem. Placement is here. Base is not 0, it's RBP. And we are putting it. Oh. Yeah, that's correct, because encode is taking the RM as the last argument. Yeah, that's. Yeah, okay, so this should generate. It will set the RBP to be as the PS RM here in the mod RM thingy, which means that we should hit this. Oh well, by the displacement is. Oh, displacement is 32. So this is the special case, right? Because this only works if the displacement is 0, 0. So yeah, that's the case when this thing doesn't work. That's the case when this thing doesn't work. And the question is how I should make the API, because there is a valid case for these. Obviously, there's a case for these. For this one. But if we would force the indirect, yeah, I think I know what I need to do. I think I know. Okay, so this one is valid. And keep this one in here. It's actually. It's RBP in the output, but that is because I think it's set to 64-bit mode, and then RBP is always RBP, I guess. But we can make a note, and we will find out why in this assembler it says RBP instead of EBP. There's probably some rule about this, because RBP is special register for different things that I don't know about. Yeah, I'm not fluent with these things, but I will one day. Will happen soon. Anyway, I will need to find out why is it so, and this case is different one. So if I say RBP here, then it makes sense as long as I provide the displacement. So let's try what will happen, because you can see here, in here, it only works if you provide the displacement. If we don't provide displacement, or say that, hey, we don't have any displacement, then things will happen. And those things will happen that actually it will still expect 32-bit placement to pass that. It's documented here. So if we set mod RM to 0 and set EBP for RM, it will expect another 32-bit displacement value. Like it will force, that special case will force it, and what it will produce is this one. It's like a special case that is that you can use to read address relatively to your current location. And the current location, at least by my tests, was from the end of the instruction. So if the instruction is encoded like this one, like this in the memory, and it's starting at 4000, it uses 6 bytes, so it will end at 4006. Then we add the displacement to that address where the instruction we are just calling processing ends. And we will get final address, and we will read from this final address 32-bit value. So it allows you to read in relation to the instruction, to the program pointer, which is quite interesting. I don't know what the actual use for that is. Probably reading from stacks and things like that might be useful. But for that, I would just I don't know, use ESP or push the EBP and set the ESP value to EBP and use that. I think when you are using EBP, it produces back reading for local variables, produces less code, less bytes per instruction. But we will see that. We will see that. So there is this special case that in case the EBP is used as RM and this is 00, it will still expect the 32-bit displacement, even though documentation says that whenever you provide this value, it expects 32-bit value. But if you provide this one, then it does, then it doesn't expect anything. So only in case it's this and the register is set to EBP, it will actually force you to use a 32-bit displacement after it. And the question is how to encode that, because this is valid, but let's give it a 0 here. This is somewhat for the future. We'll keep it in the future things. And now we want to produce that one. I guess if we will produce whatever we will produce, it will be this. And I can try it in the disassembler. Yeah, and it just outputs garbage. Yes, that means that this is invalid variant, and we can detect this. But we can also be explicit about this, so we can say that because this doesn't have any, this is the base register, and this doesn't have any base register. So we can be explicit about it and say that, hey, it's a none. So there is no register and no base register, and we want to provide something. But then what if people will just actually know about this feature and will try to force RBP here and the 0 value? Because they, for example, want to read what is exactly after this instruction that we are running. Will produce garbage, you know. Thinking about how to do the APIs, because one thing is that I might know, but I will forget quite quickly about these things. Really quick. So I think this should be invalid. Yeah, this should be invalid because you cannot express it. You probably can express it, but we will have to go further. But for now, let's say that we can validate that variant. So if the x64 RBP and is 0, then we will error. Yeah, so in this case now this should fail the error. Yeah, it will fail on that error. Okay. This is none. We can allow membase now to be 0. And if it is 0, so if s membase is x64 none 0 actually, then we will force this .rm. I will just note because this mode can be used then for other things as well. I don't think it can be used with PP, but that should be okay. So we will force for this thing. Probably do it even like this: x64 mod rm indirect. Yeah, it needs to be even handled here. So there should be two things to this. We should. Leave this. Set them to zeros here, and I will put all the instruction outputs here. Probably rework it like this. And then we need to especially handle the mode because we are forcing it a little bit different. So in this case, the mode can be whatever was there. So in this case, we can encode the for one is this 8 case 4. Probably pull this out somewhere else to a different function. I'm still trying to find out what the best structuring for all those decisions you can do and all those exceptions that you can do there, what they are. So in this case, if the base is 0, but we don't want any base, and index is 0 and scale is 0, and yet we still are using the mem, that means that this is the special case where we need to set the set these here. Start like this are the default value. Set this to -1 and here. x64 check mode is greater than 0 and mode is lower than 4. There is the maximum value actually. Register is greater than 1 and RM is greater than 1 and 0. It's unsigned. Oh, okay. Yeah, because we don't need that many. This happens. Right. This not RM register and not RM. This one. Here, if the base is not 0, then we must check if it's RBP, and if the displacement is 0, then it's an error. However, in this case, the base is 0. Then we basically force the displacement to be written without actually changing the mode. This is actually a special case, and eventually this will turn to be a default case. Because we will handle also index and scale within this code, and this will become default, and this will be a special case. The displacement size is now 4. We will output the displacement even though the mode will be indirect, so we can check whether this code will actually jump there. And we also need to make sure that the mode RM register is set to RBP. Not sure if I should set both of them or just one, or whether I should use the mode RM here, because yeah, this is not correct. One should be here together with the none, because we need the none. We need none. Actually. Probably do it even like this. Yeah, I like this. Placement and the placement size. this is where? This is here. Yeah, we need to check. Here they come as zeros. That's okay. What the fuck happened? Kind, register, memory, and we lost the break. But we didn't go here, so the only test we have. This needs to be this. Good. Placement is 0. Yeah, this will be pass. Yeah, we'll set this one to 5. Placement size to 4. Load was -1. Set it. Yeah, we need to set it to correct. Yep, be there. Oh. So this is what we use, and that should be correct. Yep, it's RIP. Oh, interesting. Because this is the register for instruction pointer actually. It will actually display like this. I think. So there is an option to actually not use none, but defined RIP. I satisfy that here. I will need to check that. Because that's actually a nice way to say it, because it is really. After it's ready and processed, then RIP will point after this instruction, and that's where the offset would be. Yeah. Okay, that's quite interesting. That's interesting. I will have to note these in the write-up. This is interesting that it actually treats it, because the documentation doesn't say anything about that as far as I know. So if you say, if you look into the instruction format part, instruction prefixes here, and if we go this table, this one's, it's not, it's 32-bit, this one. So we are setting the register to whatever, but the mode is 00 now. We are forcing it to be 00, and we are using this value, this which would be EBP. But it says here that the effective address is this 32. And the note says denotes 32-bit displacement that follows blah 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 blah, and that is added to the index. But we don't have any index here, so it doesn't explicitly say that, or at least I haven't found it, that it should be this register, RIP register. I wonder what actual register numbers are. Instruction prefixes, placement immediate. Yeah, because it says that the register, it uses these codings for registers, but it never says what actually all the registers are. So I guess there will be some kind of a list somewhere of basic architecture, data types, instruction pointer. It's this one, it's instruction pointer that we're talking about. RIP register. This register holds the 64-bit offset to the next instruction to be executed. So when we are executing the instruction, RIP will be already on the next one, which means that that's why the offset is after the end of the instruction. That's awesome. But I would like to know basic program execution register, general purpose registers. Yeah, so these are here's the IP, the basic ones. These are segment. This is the architecture. Yeah, doesn't say any what the values are, whether they are somewhere assigned to them or not. Okay, I will probably do it right now, even. Yeah, I will do them. Yeah, we will keep none because it will be used for index. Really, we want none, but we want this one to be special one, and we can finally. X64 check register. We'll give it register and it will just call whether the register is smaller than that. Has to be equal to 0. Greater equal to 0, which is none, and I will just not have the first last thing. Need the last one to be lower than that, and then we will have special case register. And we can probably use it somewhere else because we might be able to read the RIP, for example, from LEA. Maybe it will allow us to somehow read this register, and maybe that construct that we have there is actually that thing that is used to read the IP register. We will see. So I will this thing if it's RIP and the only place we will use it for now, but maybe they will. Okay. And finally we need to check the register here. This one, because this is the most important part. And this is already decreased by 1, so we need to increase it by 1. And also update the macro to accept expressions, not mess up anything. Some weird ones will operate. I think so. This is 70. Yeah, so it passed here for some reason. Go and this. 3, 4. 16, and this will be 7. The fuck. God. Okay. Code RM is 20. And actually, you know what? I will just pass the here, and we'll do the decrease in here by 1. Because that way we don't have to care about those things, and we can just treat them as normal registers. And it will be, this will be, this is actually x4 mod rm mode. You can set it to -1 because C doesn't give a fuck. Help us anyway. But we still need to check the ranges anyway, so that's all right. So that means that we will set it here, pass it here. We don't have to do the -1s at all. It will simplify the code. Because I think we only are dealing with the actual register numbers. And this is set to RIP still from somewhere. It's for which one? It's for this one. So we didn't go through this. Interesting. So let's see. It should have gone through. Not for. Yeah, it's because that's 0. Because now it's not 0. So it will go through here. And that's why it fails. But this is the normal case. So what we can do else, we can go here, paste this. I'm not processing the index for now. This will go. Yeah, it's still the same thing, and it works. So this is RIP plus. And this is what we expect from it. Uppercase. Okay, so we have covered at least one special case. There's still one pending, and we need to still test the previous. Hello, Crixano. And we are failing. You jinxed me, Crixano. Why did you do that? Why would you ever do that? Whether you're still there, I was busy looking into the code, so I'm a bad streamer in this way. In all the ways, actually. We will go here. Reg, that's okay. And it fails. Yeah, fails because of these two. Regs. It's not Regs. Jinxed me, man. Why did you do that? It worked just seconds before you came. Okay, it works again. Okay, so you unjinxed me. That's because I called your jinx, and that's what happened. So I solved it, not you. Okay, so we have these. That's okay. So let me put. Okay, and we need to also do. Yeah, this is +0 version. So we will also do the 400 version. 0, 0. And we need to do the version. And that's like this, I think. You see? I need to stop writing these here. Yeah, it works. It works, and let's run it through the assembler. I just hope that a pair of Volksen won't come in, because if he will laugh his ass off at what I'm doing here. Yeah, this is correct. Okay, so that's correct. Okay, so not today, but probably tomorrow, because I need to take a little bit of rest. I will a little bit talk about that. What I will try to do tomorrow if I get to stream. So tomorrow, today I went through what we went through today. We went through. Basically, we're here. Alright, the scroll bar. We are in the middle. Let's be fair. We are in the middle. So we have covered almost every special case, which is just the one, but every case otherwise of normal use of this mod RM thingy, which is this second byte. So if I repeat it, it's opcode mod RM thing. Opcode is just 1 byte. Mod RM is a second byte that follows the opcode. In case the opcode requires it, it's not always required, because there are some opcodes that don't require it because they find what operands they use, if any. For example, red doesn't have any operands, so they would have mod RM. But there are some that require mod RM. In this case, we are using the two that are for MOBA, and that's these two. And these two require RM because it says here. So mod RM can do all these things that we actually finished today. Assigning register to register, and then everything else is basically assigning contents of a memory address given by either register or register with displacement, or directly. We don't have one more case. We are missing one case. Missing that one. No, it's this one. Yeah. Okay. Okay. And this one is. Yeah, we need to retest this one because it needs to still work. Yeah. We don't know whether it works, but if we will take this code and put it into disassembler. I'm sorry, I was in the middle of finishing this and failed that. So this works correctly. It says RBP, not EBP, but this is probably because it's already switched to, like, this one is working in 64-bit mode. Yeah, I switched it to 64-bit mode. In that case, it means it's using RBP special register. But I will keep it here and we'll try to find out why it's that. Exactly, because how special the RBP register is, what it does, and why it's always 64-bit on 64. The other ones being 32-bit. Okay, so we have this case as well. So we have all the special cases when using mod RM, except for one, and that one is that in case ESP we pass. In the mod RM, the RM parameter is ESP and the mode is 0, 1 or 2. In those cases, this is basically a special case that will say that, hey, there is another byte. So it's not only these two, but there is a third one, and it's called SIB, which is scale index base, and that's why it's SIB. And this additional thing, this additional byte, provides additional fields, and it basically provides additional addressing modes that go like this. So you can do simple expressions in here with registers. So you have base register, index register, optional scale, which will multiply the index register, and then you have a constant or immediate value for displacement, which is the same deal as we had before. This displacement is the same thing, and it's still controlled by mod RM mode. It just with SIB you will get these three additional things that you can use. There are some. It's quite straightforward how you encode that. Like scale is just 4 values, and we already have scale for it. Scale here. These are the 4 possible values: 0 for times 1, 0 1 for times 2, 1 for times 2, 2 for times 4, and 3 for times 8. So this will give us the scale. The index is just a register number. But again, there are 2 special cases. One is for when you don't want to provide any base register. So these first ones, if you don't want to provide any of those, you just say it's EBP again. We are again using BP as a special value. And it works only in if the mod RM mode is 0. And I guess there is some relationship between what we did for RIP here and RBP's cases. Like this special case basically goes along next to SIB and has the effect. So I want to actually discover, or maybe think about during the implementation next time, what it does. And final special case is no index, so you don't want this index thing, this register here, and in that case you set it to ESP, and that's it. In our documentation or our API, we will use simply none for those. It will be none, which is basically 0, so we can keep it as 0, so we don't want index or base and get there. So we'll probably have to somehow reuse this RIP thing, or we will have to have like a special value for none, so we can get to this special thing. No base, but we have index and placement 32-bit, and this also forces it. We'll probably go through the same yeah, it will go probably through here anyway, and maybe we have already somehow made it work. In this case, we will see what happened, and that should give us correct output for all the combinations of all possible registers on the 32-bit x86. Basically, we are still focusing only on x64. We are not going to do 32-bit version of this thing at all. It will be 64 because it makes much more sense. It has more registers. We will yeah, and once we have the 32-bit addressing, we can bump it up to 64 by actually adding yet another byte that is called rex rx, which allows us to supply additional bits to every register in these 2 bytes that are using registers, and it allows us, rex byte allows us to add 1 more bit, so we are not, because now the using 3 bits per register number. Not enough for these additional 7 registers that we for with platform. So that's what's next. Next is basically SID, and probably we can make it to REX, and then we will be just writing tests for a while. I will try to write the tests where we have them ready, at least here. Not completely correct, but at least we will see all the possible cases that we have. And by what I've seen from the Intel documentation in the, because this is supposed to, this section, where are we? Volume 2, and instruction format for protected mode, reliable mode, and virtual mode. This should cover everything, and we already went through those. There are some prefixes like lock and these things that we are not dealing with, and all the prefixes we are only going to use one, that is REX, for switching to 64-bit mode, but otherwise we should have covered the whole section here. The whole section is now covered. We will eventually get to like floating points and vectors and all these things, because I will need them for my implement application of the thing, but yeah, so that's still a discovery, so I have no idea how that shit works, so we'll see. Okay. Somebody's writing to me. I'm in computer information technology degree program right now, but I cannot learn coding to save my life. I'm trying to learn Lua right now for game script development. Any recommendations? I have the syntax down, but when I go to write the code, I just stumble and don't understand. Usually it helps to visualize things, so you will generally go to go and try to do something that is really, at least it helps me. I'm a visual person, and it helps me when I see everything, how it goes. That's why, for example, when I'm programming, I want to see that the values are there. That's why I go through the debugger and go line by line and see what is happening. So it maybe help you that you will first try to do something visual, like a game or something simple. And for Lua, like especially there is Love2D. I will write it down. Love2D framework that has some examples and good documentation in general. So it's this one. And this is actually game framework, but simple 2D game framework. They can do 3D as well, but it will allow you to write Lua code and actually see things. You can print things. You can try all these special constructs like control flow, or for control flow like for loops and while loops, and putting things together, changing the positions on the screen, and you learn better this way, I think. If you turn the learning to play, much better. So I would recommend that, if I could recommend anything. If you are not a visual person, then I can't really help you, because I would be just guessing what non-visual person would be doing to learn things. So yeah, try Love2D, try to find, there might be even some tutorials. Yeah, for example, this one will help you how to set it up, and it was just simple search on YouTube, but it might give you some idea about where to start, how to do simple things and work your way up using just simple things, because it's always like that. It's always just simple things on the bottom, except it's a lot of simple things on at once. So okay guys, thank you very much for watching, and I will try to stream tomorrow a little bit, because I'm really pumped about this. I really can't wait when we will be able to actually run at least really simple codes that we generate by just calling a C function, like forcing a pointer to some memory that is executable where we have just put our code and then running it. That should be awesome. Yeah, I'm messing with code too much actually, and it's really hard to go online. But today it was a kind of a good topic that I could actually split a little bit and had the preparation, so I knew what I will be doing. I kind of thought that I will get through SIB as well, but this is kind of interesting. So I think it will be more interesting when we will be able to run some code or generate some code, like doing loops and shit in memory and then running it, so we don't have to use scripting or that, but you just generate assembly code from your C and then run it. CPU speed out of it. Okay. Thank you very much, guys, and I will try to stream tomorrow. Hopefully, I won't have terrible daily job things to do, so I won't be tired as usual. And we will see. Thanks, guys. Bye bye.